totally gonna dress up today, but but my costume isn't ready.
Wait, for the electron affinity, you want to go on
Electron affinity. That definition. It's a good definition that they have there for it.
So you want a neutral atom nations.
All right, so we talked about this thing called ionization energy. And ionization energy is opposite of this. Ionization energy is energy needed to pull out an electron. Okay? This tells you the energy that an atom gives off when it accepts an electron. Now down below here, I have in parentheses a negative sign. And what that means is its energy is released. So a negative sign means energy is being given off, okay, or lost. So that's why they put it as negative. They put it as negative because let's say that I'm standing outside in the cold and I'm sitting there and I don't have much on it. I am losing energy. Energy is going from my body to the outside air. If energy is going away from me, I'm losing energy. So my whole system has now lost energy, and so that's why it's a negative number. So when energy is lost by what we call a system or reaction, that means there's energy given off. A lot of times it's as heat energy. A lot of times that's heat energy that's given off. All right? And that heat energy we can go ahead and measure. Now, negatives have higher energies given off. All right? So if it's a negative number on that page, it means it's giving off the most energy when it accepts an electron. So what element on the periodic table gives off the most energy when it accepts an electron? Jared?
Chlorine.
Chlorine. What's next? Yes, Eli. Fluorine. What's next? Bromine. They're up here, except for fluorine. Okay? So these are very reactive. They would break. They would instantly react with things around them. Okay? And why would they? Well, they all want electrons. So anything that's willing to give up electrons, they'll take it from. So I was working with this stuff one day and just really didn't think of it and was working with it. And I had gloves on, and I had goggles on, And I was working with it. But as you can see, it turns from a liquid into a vapor pretty easy. If you look on the periodic table, this is Br, it's a liquid. But above it, you got a gas. So its boiling point is really, really low. Boiling point of 265, or no, I'm sorry, 332. So that would be about 60 degrees Celsius, which it would boil. Well, room temperature is 25. And so it would evaporate, okay? And it was evaporating, it was contacting my skin, and my skin started to itch, and I knew something was not right. My skin should be itching right away because of that. It started burning and itching and that. Because what it was doing is it was picking up electrons from my skin. Okay? And that's not good. Alright? So when we say things are corrosive or to the touch or will affect you in a way, probably going to be taking electrons from your skin, whether it's the tissue of the skin, moisture, water in the skin, whatever it might be. So, as you go across, what is the general tendency? Now, there are some zeros there, which means they're not going to give off any energy. So, there are 3 groups with zeros, page 157. What groups have zeros associated with them? Jared?
Group 2, 12, and 18.
Okay. So groups that have 0 affinity, you can write those in, would be groups 2, 12, and 18. Does anybody know why those particular groups, according to electron affinity, have 0 affinity? Yes.
Would they all have full, like, one of their subshells?
Yeah, they all have full subshells. So S is S2. And S2, they would have to create another subshell to accept an electron. And so there's no room in the end. You've heard that before, right? Christmas is coming up. There's no room in the end. Sorry. We don't have any rooms left. Okay? So D, there's no rooms because they're all full. No room. Alright, and then you got group 18. Of course, I'm not going to draw that. But group 18 has 3 in its subshell. No room. It's full. Alright, so there's why there's a 0 affinity. But you look at the group right next to it. It's called bromine, chlorine, fluorine, iodine. They have extremely high electronegativities because group 17, guess what? Let's get one more and we'll be stable. One more is all we need. So it looks for that one more anywhere something's willing to give it up. And we'll look at a couple examples today. I have demonstrations where we have a transfer of electrons because one's really wanting it and taking it away from something else. And that's what causes reactions. So the reason we're studying group and period trends so we can understand what elements and why they are reactive and what they want or what they're willing to give up. If you take something with a low ionization energy like francium, francium is, when you look at the group trend, this is the lowest ionization energy, which means it's easiest to take out an electron from francium. You pair it up with chlorine, and it's not going to be fun to be in the same room when that happens, if you got a larger amount of them. Because chlorine wants, and francium says, here you go, take it. And then, so lots of energy, because you can see chlorine, when it accepts an electron, it gives off lots of energy. And you don't have to get much energy to get francium to give it up. Okay? So we have those extreme cases, and then we also have cases that aren't so extreme. But the electron affinity, if you want to write it down, what's the group trend? We should do period because that's the first one that's listed, right? Mm-hmm. So what's the period trend? Well, there is a general trend. There are some that will not, if you exclude the zeros, okay, and we know why those zeros are what. Now nitrogen can be 0, 2, and I'm not going to go into why that is, okay? But as you go across, what is the general trend across the S's and P's? It's bigger. There's more of a likelihood that that atom's going to gain an electron. So it gets larger. Okay. Now with these trends, it's pretty easy to remember because you only have to remember one. So if the period trend is the increase going across, the group trend is always opposite. So the group trend is what?
But some of them increase too.
Some of them do, but if you look at general characteristics as you go down, they're going to decrease. Okay, there are some cases where they don't, but if we had to come up with a consensus what a trend would be, we would say that they decrease going down. Okay, decrease going down. Any questions with that? Okay, so it's more likely. Now, again, we got to take out those exceptions, but we know what they are, and we know the reason why they are in that place. Okay, I think everybody knows what a full subshell is and knows the reason for that. So I'm going to go ahead and give you a reason for electron affinity and why that is, and then we'll move on to the last one, which is electronegativity. Okay?
Is this for the period or the group trend?
Period. That's for the excuse me, that's for the period.
Is that re-tease?
Release.
Release? Oh.
Electrons being added closer to the nucleus of an atom, which causes a release of more energy. The group trend, they're being added farther from the nucleus, so it's the opposite effect. We might state it just a little different, but basically the electron that's being added is added to a region that is farther from the nucleus. And because it's farther from the nucleus, there's a less attractive force for that electron to be pulled in. So that's the group trend. I'll write that down here in a second. And then we'll look at electronegativity. If you want to turn to electronegativity, page 161, that'll be our next thing. But I'm going to put the group trend reason here in a second. Just want everybody to have a chance to write that in. So the atom's larger when that electron's added. There's There's less attractive forces, and because of that, we'll have a production of the lower amount of energy that's given off. Okay? You guys go ahead and write down your trends for electronegativity. So look at the numbers. Look at the size of the numbers, see what's happening going across. We don't look at D's, remember, we just look at S's and P's, so we skip the D's. Write down what you think the trend is, and then do it for the group. What's the group trend as you go down? And look at that trend. While you're looking at the trends and got those written down, because this is pretty self-evident, go ahead and write the definition for electronegativity. It's going to be similar to electron affinity. They have similar characteristics, similar trends. But this is after the atom is bonded. So the atom's bonded to another atom, and then there's numbers associated with each atom that indicates how much of an attraction that atom would have for a shared electron. So there's some sharing that takes place between atoms when they bond. And when we take a look at that sharing, the number that's shown or given to us, called electronegativity, tells us a little bit about the share that atom would have compared to another atom relative to it. Okay? So you got that definition written down, group and period trend written down. All we need to do is the reason for that, and I'm going to give you a little bit of explanation and model of this kind of taking place. So what is the period trend? Increases. Group trend? Decreases. It's pretty easy to know once they're always opposite. If you get them mixed up, then you're in trouble when you have to answer questions with them. So what do we mean by attracting? All right, so we got a chemical bond that happens. All right, so we got a chemical bond that happens. Let me show you with the model, kind of a sharing of an electron, kind of how that works. I'm going to put in, down below here, I'm going to put in fluorine, and I'm going to put its outer shell. No one won't show the inner shells. But fluorine is pretty small, relative size. Okay, there's fluorine. And it's going to share an electron, let's say, with sodium. Now, sodium will be a little bit bigger, relative size. And there's sodium. Now there's an electron here that they are sharing. Then you can tell me why you think fluorine has a 4 where sodium is like a 0.9. Look how close it is to the nucleus. Look how close that electron is in proximity to the nucleus versus the sodium and its nucleus. It's a proximity based upon the size of the atom. Okay? Because the electron's closer to the source that's pulling it in. So it's going to be a stronger share. It spends more of its time close to fluorine than it does sodium. Okay? maybe an analogy would be, growing up, or maybe you have a friend and you guys are really good friends. They may spend a lot more time over your house than they do at their house, maybe at times. And so because of that, there's a greater share there. Okay? So, I'll give you a reason here for a second for group and period trends, but that is a very good way to show that they have equal attraction. So, fluorine has a greater attraction than sodium. So fluorine's greater than sodium when we take a look at attraction. We can tell that by the number. Right? We can tell that by the number. Okay, we're going to finish up this concept, this idea, and then we're going to do a demonstration where we can show some of these things taking place. Okay? With those characteristics. So we'll get that written down for you so that you have it. And then you can put your notes away. Probably on Monday we have an assembly, and we might not be here the whole period. But whenever we're here, you're going to take your notes. There's a portion of the notes we haven't finished, and we're not going to finish them until probably Tuesday, so I can go through it with both classes. That's when it talks about ionization energies and that. So we'll finish that up later. Okay? So period trend. Reason.
So is that like saying that it's easier for the smaller atom to get close to another atom to share it?
Share the electron.
Yeah.
A lot of times it has to do with the size of the atom. And then once you guys have that one, I'll put the group trend, which is kind of the opposite of this. A lot of these are opposite. So I'll put that down, and then we'll go ahead and show the demonstration.